Page 4 of practice exam 3 is a very complicated question. This could be done strictly based on visuals. I gave a little bit of a description here for those of you who prefer written questions. All right, but I'm just going to go to the picture here to try to show you what you should be focused on when you see these kinds of questions. Now, this is a very difficult question. All right, I don't think there's a question that's this complex on your exam. All right, but this is still doable. All right, this is a good sort of advanced homework question. All right, so first off, you'll note that both compound C and B contain a beta keto ester. All right, and a beta keto ester should scream to you Claisen chemistry. Now, in this particular case, it's an intramolecular Claisen reaction or a Dieckmann reaction. Okay, but when you have a beta keto ester, it means that you had an ester-derived nucleophile and you had an ester electrophile, okay? And what happens when a carbon nucleophile attacks an ester? The alkoxy group on the ester is going to leave in an addition-elimination reaction, okay? And so, what the hell was leaving? Well, I've given you the chemical structure of the starting material and both of the products, and you'll note that each of these has lost an oxygen, a carbon, and 4 hydrogens. All right, so this has lost a methanol in both cases. All right, so you'll note that these reactions are very similar. All right, the only difference, the products are very similar. The only difference is what's at the alpha position between both carbonyls. Okay, and what is on those hydrogens highlighted in orange. All right, so you'll see there's an extra methyl group in different positions on both B and C. All right, and so what happens is this is a diester where the two esters are both enolizable. Okay, one of them is forming a quaternary center at the alpha position shown here. Right, this is quaternary, right there, right, and this is only tertiary. Okay, so this is going to come from, I'm going to try to fit it in here. That's the cyclohexane ring that's unchanged. All right, now for this first one, this can come from a methyl ester that looks like that, all right? And then attached to the ring also, there's a methyl group there. Oops, that's an oxygen. O-methyl there, all right? So this is a diester. The same molecule has 2 esters, all right? So this can do intramolecular Claisen, all right? So the question becomes, you know, if we form compound B, it means that we enolized here, okay? To form compound C, it means that we enolized here, right? So what's the difference between those two enolization events? The difference is in the enolate stability, right? So this is a kinetics versus thermodynamic stability or preference question, all right? So the green position is less hindered. It's got more protons on it, all right? So this is going to be kinetically favored, all right? Remember, enolizing there is going to take us to C, all right? So there is a kinetic deprotonation event. Kinetic deprotonation means LDA, okay? Enolizing at the blue position is what gets us over to B, all right? Again, to form the more substituted enolate, we're going to use a thermodynamic base. And of course, your book prefers to use sodium hydride. Okay, so I think that's the toughest part of this question. All right, it's an intramolecular reaction. You've got, the added complication of multiple things coming from one molecule, plus the description. So we know from all the examples that we've worked in class that when you have a beta-keto ester, you can hydrolyze the ester, heat it up, decarboxylate, form an enol, which tautomerizes into a carbonyl. In this case, it's going to be a ketone. All right, so the final product here, so we do the decarboxylation, which means our ester is going to go away. Our ketone stays, and we end up with a methyl group at the alpha position. Okay? So, as it says in the description, if we just treat compound C with acid and we don't heat it, again, this is going to hydrolyze the acid, or excuse me, the ester into the acid. So this is going to give us something that looks like this. Okay, and so I've drawn the acid with the OH group towards the carbonyl. And so you should all look up in the book what the transition state is for the decarboxylation step for the bonus question here. All right, so basically all that's changing between going from C all the way to D is it's a stepwise version of the question that's asking how do you go from B to D without all the steps in between. All right, but you should definitely be comfortable with this at this time. We've talked about it quite a bit.